Welcome to our exploration of a pressing question in today's climate conversation. Can we reverse climate change through the controversial arena of geoengineering? In this video, we will delve into the different methods of geoengineering, from solar radiation management to carbon dioxide removal, examining both the potential benefits and the significant risks involved. We will also highlight the ethical dilemmas and public perceptions surrounding these technologies, as well as the importance of global governance in their implementation. Join us as we navigate this complex landscape and consider the future of geoengineering research in the face of climate urgency. 1. Understanding geoengineering. A brief overview. Geoengineering is an umbrella term for a range of technologies designed to intervene in Earth's climate system. The two primary branches are solar radiation management, SRM, and carbon dioxide removal, CDR. SRM aims to reflect a small percentage of the sun's light back into space, while CDR focuses on removing CO2 from the atmosphere. Both approaches are still largely theoretical, but they hold significant promise and peril. The concept is like using a massive thermostat to control Earth's temperature, but tinkering with such a complex system is fraught with uncertainty. 2. Solar radiation management. Reflecting sunlight. Solar radiation management involves techniques to reduce the amount of sunlight reaching Earth's surface. This could include injecting aerosols into the stratosphere to create a reflective barrier or deploying mirrors in space. The idea is similar to wearing a sun hat to cool down on a hot day. However, the potential side effects are a major concern. SRM could disrupt weather patterns, affect agriculture, and lead to geopolitical tensions over who controls the global thermostat. Moreover, it doesn't address the root cause of climate change, greenhouse gas emissions. 3. Carbon dioxide removal. Cleaning the atmosphere. Carbon dioxide removal focuses on extracting CO2 from the air and storing it elsewhere. Techniques include afforestation, ocean fertilization, and direct air capture. Imagine it as a giant vacuum cleaner sucking up excess carbon. While these methods are promising, they are not without challenges. The scale required to make a significant impact is enormous, and the costs are high. Additionally, the long-term storage of captured carbon remains a technical and environmental hurdle. 4. Potential benefits of geoengineering. Geoengineering offers a potential safety net if other efforts to mitigate climate change fall short. In theory, it could quickly lower global temperatures and buy time for reducing emissions. For countries already experiencing severe climate impacts, such as rising sea levels and extreme weather, geoengineering could provide much-needed relief. It could also spur technological innovation and create new industries. However, these benefits must be weighed against the risks and uncertainties involved. 5. Risks and uncertainties involved. The risks of geoengineering are significant and multifaceted. Unintended environmental side effects could exacerbate existing problems or create new ones. For example, SRM could lead to reduced rainfall in some regions, affecting agriculture and water supplies. There's also the ethical dilemma of who decides when and how these technologies are used. Furthermore, geoengineering could create a moral hazard, reducing the urgency to cut emissions and transition to renewable energy. 6. Ethical and moral dilemmas. Geoengineering raises profound ethical questions about humanity's relationship with nature. Is it right to manipulate Earth's systems on such a large scale? Who gets to make these decisions, and who bears the consequences if things go wrong? These questions don't have easy answers and require global cooperation and governance. There's also the issue of intergenerational justice, how our actions today will affect future generations. 7. Public perception and acceptance. Public opinion on geoengineering is divided. Some see it as a necessary tool in the fight against climate change, while others view it as playing God with nature. Public awareness and understanding of geoengineering are still limited, which can lead to skepticism and fear. Effective communication and transparent research are crucial to gaining public trust and ensuring informed decision-making. Engaging with communities and stakeholders can help address concerns and foster acceptance. 8. Global governance and regulation. The need for international cooperation is paramount when it comes to geoengineering. Without global governance, the unilateral deployment of these technologies could lead to conflict and inequality. International treaties and agreements will be necessary to regulate research and deployment, ensuring that actions are transparent, responsible, and equitable. Existing frameworks, such as the United Nations Framework Convention on Climate Change, UNFCCC, could play a role in shaping governance structures. 9. The future of geoengineering research. Geoengineering research is still in its infancy, with many unknowns and technical challenges to overcome. More research is needed to understand the potential impacts and refine the technologies. This includes small-scale field experiments, computer modeling, and interdisciplinary collaboration. As research progresses, it's essential to balance innovation with caution, ensuring that ethical and environmental considerations are at the forefront. The future of geoengineering will depend on the collective choices of scientists, policymakers, and the public. In summary, geoengineering is a complex and controversial field with both potential and peril. As we grapple with the realities of climate change, it remains an area of intense debate and research.